Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on January 30th, 2026, about 5 days ago. It introduces TEON, a new optimizer that outperforms the popular MUON method by extending gradient orthogonalization from single layers to higher-order tensors, capturing correlations that were previously ignored. The paper is titled TEON, Tensorized Orthonormalization Beyond Layer-Wise MUON for Large Language Model Pre-Training. And as we'll see later, the results are really promising, showing consistent gains in perplexity across both GPT-style and Llama-style architectures. Alright, Figure 1 immediately backs up those claims with results from pre-training a GPT small model on 10 billion tokens. The chart compares validation perplexity, where lower is better, across 3 different orthogonalization methods listed at the bottom: U, Jordan, and Polar Express. Clearly, the blue bars representing TEON are consistently lower than the orange MUON bars in every single case. For instance, using the Polar Express method on the far right, TEON achieves a perplexity of about 27.15, distinctly outperforming MUON at 28.57. Well, Figure 2 visualizes the specific mathematical operation driving these results, known as Mode 1, matricization. The process begins with the gradient tensor G on the top left, which represents the stacked gradients from multiple layers. As shown on the top right, this 3D block is sliced into vertical vectors called column fibers. Finally, the bottom section illustrates how these fibers are unfolded and arranged side by side into a single large matrix, allowing standard orthogonalization to be applied to the entire structure efficiently. So, having established the math in the previous figure, Figure 3 outlines the actual execution flow within the model. The process starts on the left by collecting gradients from several consecutive transformer blocks, focusing on the query, key, and value projections. In the middle section, rather than processing each layer in isolation, the system stacks these gradients into higher-order tensors, grouping, for example, all the query gradients into the blue stack. This sets up the final stage on the right, where the orthogonalization function is applied to the whole stack at once, effectively synchronizing updates across layers. Alright, moving from the method to the results, Figure 4 tracks the training loss of a GPT small model over time. The left panel, labeled Early Training Phase, covers the first 800 steps where the blue TEON curve drops significantly faster than the orange MUON baseline. This initial gap highlights the faster convergence. Then, shifting to the right panel for the late training phase, the plot zooms in on steps 18,000 and beyond. Here, despite the noise, TEON consistently maintains a lower loss, confirming that the benefits persist effectively until the end of training. Okay. While the previous curves focused on the small model, Table 1 expands the evaluation to GPT's small, base, and large sizes. It compares validation perplexity across 3 optimizers: AtomW, MUON, and TEON. Across the board, TEON consistently delivers the lowest perplexity scores, which you can see in the bolded far right column. For example, looking at the GPT large section at the bottom, TEON with Polar Express achieves a score of 18.73, clearly beating MUON at 19.26 and AtomW at 27.31. Well, having seen the GPT results, Table 3 now shifts the focus to Llama-style models trained on the fine web dataset. The columns display results across 4 model scales, ranging from 60 million up to 1 billion parameters. Looking at the rows, we see that TEON consistently achieves the lowest validation perplexity against AtomW and MUON at every scale. For instance, in the 1 billion parameter model on the far right, TEON reaches a score of 10.84, distinctly outperforming MUON at 11.19 and AtomW at 14.38. So, to explain the design choices behind TEON, Figure 5 analyzes the alignment between gradient vectors. The top row looks at the same component, like query or key, across consecutive layers. Notice how the blue lines, representing right singular vectors, stay high near 1. This strong alignment confirms that cross-layer correlations exist, justifying the Mode 1 strategy. In contrast, the bottom row compares different components within the same layer. Here, the connections fluctuate wildly, which is why the method stacks the same matrix type across layers instead of mixing them. Wrapping up, 2 takeaways stand out. First, treating model layers independently misses valuable structural information. By optimizing gradients as higher-order tensors, TEON captures cross-layer correlations that layer-wise methods like MUON simply ignore. Second, this approach yields consistent performance gains across diverse architectures without increasing computational cost. It suggests that future training recipes should definitely look beyond the single layer. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.